Okay, thank you very much for the introduction. And first of all, I would like to thank the organizer for inviting me to give this talk. And you are lucky because I'm going to talk about the same thing as Catherine, slightly differently. So if you understood everything about Catherine's talk, you can have a 20-minute nap. Okay, so I will follow more or less the same plan as Catherine. So I'm going to talk about TDA. I'm not going to spend much time talking about what is TDA because Catherine gave a very good introduction, but roughly the idea is that we can get some very interesting information and feature from data in general, and they can be used, and they are more and more used in some further machine learning on AI process pipeline or workflow. And in general, they are used in two different things. So I would say the simplest and the more natural one, and maybe the first one historically, was just to try to get these topological features and use them as standard features in some machine learning pipeline. So you want to increase your set of features, the set of features you extract from your data, and then you compute some topological features, the same as Catherine mentioned, in particular this persistent diagram. I will come back on them in a few minutes. But there is another more recent approach that I'm not going to talk about, but which is very interesting and promising, is this idea that you can also take advantage of topological information to better understand some complex machine learning pipelines or networks or some neural networks, etc., using topological information. And there are some very promising recent results about this, but I think this is just the beginning. Okay, so let me come back to this TDA workflow or classical TDA workflow. So in general, you start from data. So as I'm a bit more lazy than Catherine, I directly start with a point cloud here in this pipeline. And what you do is that you build what is called the filtration in general on top of your point cloud. This is this nested family of topological spaces you build on your data set. And then you use this theory of persistent homology to get this persistent diagram that Catherine mentioned a few minutes ago. And then when you get these persistent diagrams, you encode some interesting information about your data. You have, as they come as this set of points, these small diagrams in the plane, they are not immediately well suited to be processed in some standard machine learning algorithm, because in general you need to feed your machine learning algorithm with vector data, input data. So there is a whole here, research area here that consists in trying to transform this information into vectorial representation of these diagrams that are still meaningful. And this is what I'm going to concentrate on in this talk. Okay, so just let me come back to briefly on persistent homology and the way we define it. So I'm going to repeat what Catherine did with just another example. So suppose that, so you start with a point cloud like this one in the plane, and you do exactly the same. You start to grow balls. So what you want to do when you try to get some topological information about your data is that when you just look at a point cloud as just a data set, this is just a finite set of points. So in itself, it does not carry any topological structure. In general, when you talk about topology or geometry, you think about continuous objects, continuous shapes, continuous spaces, right? When you have a finite set of points, obviously this is just a discrete set. So in itself, it does not carry, you cannot exhibit directly some topological or geometric structure. So a very standard approach, which is not the only one you can do, but which is good to get a clear idea, is to take your point cloud and then to start to grow balls around your points. And as this ball grows, you keep track of the evolution of the topology of the structure. So when you grow balls, you build a nested family of spaces. You look at this union of balls, and you keep track of the evolution of this nested family of spaces. So for example, here, when you start at the very beginning, you just have a finite set of points. And then when you start to grow balls, some balls start to intersect. And then you get some connected component that get merged together. And what you do when you do persistent homology, first you keep track of the evolution of this connected component. So at the very beginning, you have as many connected components as you have points in your data set. And when you start to grow balls, when the balls start to intersect together, you have some component that disappears, that get merged into another, creating bigger component. And when one component disappears, you keep track of the depth of the disappearance of the component in this process where you grow balls. So at this point here, I still I have decreased my number of components, but if I increase a little bit more my balls now, then again, the number of connected components disappear again because some new components have merged together. Like for example, this one and this one and this one get merged into a single one. And as you can see, some new topological event appear in this filtration. Here, we have a cycle, a hole that has been created. So by inflating my balls and looking at this union of balls, I've created a hole in my object, okay? And as I did for the connected component, I keep track of this topological event. So I record the birth date of this cycle, the moment in the filtration when this cycle appears. And if I continue to grow my balls, at some point, I get a new second cycle that appear here, a second hole, and the first hole at some point gets filled, so it disappears. And again, when I'm doing persistent homology, I'm just keeping track of the depth of this hole when it gets filled, so it disappears. This is the end of the life of this cycle, and I've kept track of the birth of this second cycle, which is still alive at the time I'm considering here, okay? And if I continue to grow the balls, at some point the second hole gets filled. This is the end of this second component. And at the very end, the only topological thing that remains, feature that remains, is just this wall connected component that does not carry any topology, okay? And what I get at the end of this process is this persistence barcode, which is just a set of interval. And as Catherine explained, a set of interval can be easily encoded as a set of points in the plane above the diagonal, where each interval is encoded by a point whose x coordinate is the beginning of the interval and y coordinate is the end of the interval, okay? And this gives rise to this notion of barcode, of persistent diagram. Okay. So, and this is something that you can, in many cases, interpret in the sense that the farther a point is from the diagonal, or the longer is a bar, the longer it corresponds to a topological feature in the filtration, in the nested family you have built, of spaces you have built on top of your data set. And the longer the bar is, the longer you see along the filtration this feature, and the closer it is from the diagonal, the shorter it is. And as Catherine mentioned, the first and naive intuition is to think that points that are close to the diagonal are prone to be noise because they appear for a very short time in the filtration. So in some cases, this is a good intuition, but there are also many examples where the very relevant information is encoded in this noise. So this noise is not just random noise in many cases, it can carry some very important information. So it's important to keep in mind that it's not always a good idea to neglect these points that are close to the diagonal. Okay, and again, I'm going to repeat things that have been said in the previous talk, that the strong interest of persistent homology is that it provides some robust features in the sense that if you have spaces or sets that are close to each other, close in the sense of the Hausdorff distance or Gromov-Hausdorff distance if you are working with abstract metric spaces, then the persistent diagram you build on top of these spaces or these data sets are going to be close in a metric which is specific to the persistent diagram. Okay? So this is just an example here. I don't want to go into formulas and many definitions, just to give you an idea that persistence is robust to some perturbation in your input data. And you have many theorems that are more like this one that depend on the way you build your nested family of spaces and the way you perturbate your data. So this is an important theorem that gives sense to persistence homology because it tells you that what you are inferring when you compute this persistence diagram, when you get this topological information. This is not something which is completely chaotic, random. This is something which is robust. You get robust features. Okay. Just a very quick mention, Catherine already told it, but it's now possible to compute. This is not just a pure math abstraction or something like that. This is something that is easy or more or less easy to compute, and there are now various libraries that implement persistence computation and that allow you to exploit them in different TDA pipelines. So what I'm going to talk about now in the last 10 minutes is about this question, the last step in the pipeline I presented at the beginning about the representation of persistent diagram. How do we transform a persistent diagram into a vector feature? So this is this part, because as you can see here, you have an example of a persistent diagram obtained from here. This is a point cloud that has been obtained from a time series, and you get the persistent diagram. And obviously, when you get this kind of object, it is not ready to get used in any classification or regression algorithm as a standard feature. So you need to do something to get a nicer representation of this object. So people have been thinking about this problem for quite a while and have proposed a huge amount of ways to convert a persistent diagram into an object living in a linear space, either a finite dimensional space or a functional space, or some space in which you can do linear algebra and things like that. So here is just a short, non-exhaustive list of some ways that have been proposed to transform a persistent diagrams. And as usual in this for this kind of problem, there is not a single universal good way to vectorize a diagram. So when you have, in particular, if you are a beginner in TDA, when you get this list of all possible ways to transform a diagram into a vector, you don't know which one to choose. How can, given your problem, what is the best way to choose? Why would you choose one representation or another? What is the best one? How to make this choice? In particular, if you are not an expert in TDA, or if you don't have a very deep knowledge about the structure of your data, it's in general not easy to get this knowing which one is the right one. So, and this is So one idea to try to help users and people to choose the right representation is coming from a very simple remark that, in fact, most of the existing representation can be seen as particular cases of a general way to represent persistent diagram. And an interesting way to see a persistent diagram, as I told you, this is just a set of points in the plane. Each point corresponds to a topological feature. But you can also see this diagram just as an empirical measure, discrete measure in the plane, right? You put a Dirac mass at each point of the diagram, and then you get a discrete measure. And in fact, this is a silly idea, but it has several advantages. The first one is that now you look persistent diagram as measures, and the space of measures is much nicer than the space of diagram itself, endowed with this standard metric. There are also some more fundamental mathematical reasons why persistent diagram can be seen as measures, because in some very general settings, you can define persistent diagram as measures directly. This is a way to define persistence, to see them as measure. The point that interests us here, the main point, is that in fact you can see many ways to vectorize persistent diagram as linear representation of persistent diagram. What I mean by linear representation is that many ways to linearize a diagram can be done in the following way. If you are given a function from the plane, or from the part of the plane above the diagonal, to some Hilbert space or to some Banach space, then you can as you see your diagram as a measure, you can integrate this functional against your measure, which is just taking the sum over all the points of the diagram of your function phi, okay? And choosing different function phi, will give you different representation or ways to vectorize the diagram. In particular, for example, the persistence images that have been mentioned by Catherine are more or less the convolution of the diagram with a Gaussian function. Okay, so for example, if you put a Gaussian at each point of your diagram, you get a function that you can see as an image, and this is a persistent image, and this is just the same as taking as phi, for phi here, the map that map a point P to a Gaussian centered on P. And then you can adjust the parameter of this. Okay? And now, the interest of this way to see this vectorization of persistent diagram is that, first of all, as you see this as a linear representation, it's pretty easy to understand the mathematical and the statistical behavior of these objects and this representation in this setting. Okay, just because you see it as a linear representation of a measure, there are some results about it. And also, this gives you a way to try to design some architecture or some methods to try to learn these representations. Because as now you see a linear vectorization of your persistent diagram as a linear representation, you can try to learn the function phi, etc. Okay? And this has been done for the first time, more or less the first time, I think, about 2-3 years ago. And now there are various approaches to try to do that. I'm just going to mention one we introduced last year, which is based on, which is just a neural network layer that we use to learn a linear representation of a diagram. And it relies on an idea which is called, which is coming from a 2 years, a work that was presented at NeurIPS 2 years ago, which is called deep set architecture. And the idea of deep set is, in this paper about deep set, they introduced a neural network architecture that was designed not to be fed by a single vector, but by a set of vectors. And by a set of vectors here, you want your network to be invariant to the order in which you introduce the element of the set. This is really a set. And it relies on a very simple idea that when you have a loss function that depends on, that takes as input on a set, so this is a function that has to be invariant under permutation of your input, right? Of the vector of your input. And then you can always write it as the composition of a function applied to the sum of some function phi applied to each of the input. So for example, if you have a function phi that you can evaluate on each your input vector, if you evaluate it on each input and take the sum, you get something which is invariant to the order you did this operation. And then if you compose with another function, then you get a function which is invariant under the input, with respect to the input, okay? And one of the theoretical motivation for this approach is that, in fact, under some assumption, you can prove that any function on sets which is invariant can be written in this way. And the idea here, when you see this kind of tools or technology, is very appealing to think of persistent diagram as input sets, and then to design an architecture which is more or less similar. We call it Persley, that roughly is implemented as the composition of a function with a sum, but to have almost all the existing representation of persistence, including some ones that are not linear. You can here replace the sum to make things invariant by something else, like taking the maximum or the minimum or the highest, largest value or something like that. All these operations makes things invariant, okay? And this is what we did. We implemented this network, and it is now available. And this gives you a network, and then for different choice of phi, kind of function phi you can use, and here you can also put a weight to make, for example, you can weight the function when you get close to the diagonal, but you recover most of the existing linear representation. So this network allows you, when you don't know which representation to choose, to try to train a network to see which one is going to choose for you for your given problem. Okay? And just let me show you an example. For example, so we used it for some graph classification problem. I'm not going to go into detail, but because it would require some other extra things. But we experimented it on some problem of orbit classification of dynamical system. So we had this dynamical system, which is a linked twist map, which is a classical one, that depends on a parameter. And we had some observation of random orbits for different values of the parameters, 5 different values. And then from these orbits that are just point clouds, this is a 2-dimensional dynamical system, we try to do some classification to recover the class, to which parameter each orbit was belonging. And this is a kind of result we get with respect to some other result. I'm not going to go too much into detail. And just in the last minute, if I have 1 minute, I just want to conclude by showing you that this is also something we have been doing a lot for a few years, is that interestingly, Tda in fact started from, I would say, from a community of people who were more mathematicians and real applied scientists. And I think many people have made some efforts to bring Tda to real applications. Catherine mentioned some very nice applications. I just want to show you very quickly, two other applications of this kind of technology, just to show you that it works in some very industrial settings. As in the case of Catherine, this is Tda applied to time-dependent data, time series or multivariate time series. So here are some examples of the time series we were interested in. These are multivariate time series. So one example was some work we did with a company which is called Sysnav. This is a French SME, and we are working with them on some the analysis of movement and activity of pedestrians from inertial sensors. So people are wearing some inertial sensors that measure at each moment the acceleration of the sensor and the angular speed. So we get some multivariate time series. And from this data, you want to understand and analyze the movement of the people who are wearing this sensor. And we do that for some medical studies in the health domain, but also in defense domain. And the idea was to use Tda to try to improve. Because when you are looking at time-dependent data, there is a huge amount of tools and techniques to deal with time series, right? And it would be stupid to not to use them just because you want to do Tda. So the strategy we have, and I think this is probably the right one, is that not to throw away all the existing things, but first do what you can do with all the existing tools, and then try to improve using Tda and get some benefit from Tda. And this is what we did, for example, in this case, to detect dyskinesia for people who are suffering some Parkinsonian disease. And the way we did it is exactly by first building some neural network to so some kind of standard neural network fed with our time-dependent data, time series. And then we added a layer in this network that was taking here, for example, the persistence landscapes to improve the technology and the result. And we got some pretty good result, including for some other kind of problem about activity recognition. I'm going very quickly. And a second example of an application, concrete application, is again, it was with ECG data. So this was univariate time series, and we were interested in detecting and characterizing arrhythmia, different kind of arrhythmia. And the way we did it again was first using a standard techniques based on convolutional network, and then we added in our network a Tda channel that was relying this time on Betty curves, and we got some significant improvement. And So that's a very nice result and a success for the industrial. But I think that, just to conclude, one interesting thing as a researcher and scientist is that when you get such a nice result, improvement, is to try to think about the reason why you got it. Because we built some quite involved neural network, it's not completely easy. And one thing I think, maybe this is a take-home message, which is important to, one of the reasons here we got a real benefit is that when you get these topological features, in general, topological information is not only quantitative, it's also qualitative. So it tells you something about the shapes, that you can deform the shape and still keep this. If you have a loop or a hole in the data, whatever the size of this hole, you will know that there is a hole, okay? And you can deform the holes, it's not going to change. And in medical application, like ECG data, where you have a huge variability between people, many features turn out to be very sensitive to this variability among people, while topological features turn out to be much more robust. And in fact, this kind of technology take advantage of this robustness of the topological invariant to, in fact, help you to improve and get something which is better when you look at generalization, etc. Okay, thank you.